Now, I think most of what we're doing, you've seen before. In today's class, what we've done, I'm sure you've seen it before. But there's some concepts in there that I'll tell you that we start with today that don't go away, and we tend to struggle with them all the way up through calculus. And the thing that's what I got underlined here, that this is the SOL that is pertinent to this lesson right here. And it's talking about a lot of things in there that are not in this lesson. The one thing that's in this lesson is domain and range, but you probably remember those words. Maybe you need some refresher on what that means. But things like zeros and intercepts and that won't be necessarily part of what we're doing today. Relations and functions. Good. Okay, there we go. So a relation, these are definitions. I've written them, the words over here. Not because, they tell us to have a word wall or something like that, but this lesson's got a lot of words in it that we do have to know, right? Relations and functions. A relation is a set of pairs of input and output, basically x's and y's, right? So now everything in chapter 1 was one variable. Now we're into two variables. Now we've got both an x and a y. So these are 4 ways to represent a relation. Ordered pairs, x, y, right? First one represents x, second number represents y. A mapping diagram would be where you have all the x's in one bubble, all the y's in another bubble, and then you draw arrows that connect. Like this ordered pair was -3, 4. That's why you're drawing an arrow from the -3 to the 4, right? Drawing an arrow from +4 to 3, right? Or you could do a table of values, right, with a column for x's and a column for y's. Or you could graph, right? We understand how to graph a point x, y, right? Remember the x, this is like an address, right, where the x is telling you how far to go to the left and the right. Right is positive, minus is negative. The y is telling you how far to go up and down. Up is positive, down is negative. Years ago, it was like 1979, I moved to Logan, Utah, right? And a lot of the cities out there, because they were planned like way later, they're not like the East Coast where you had like the Pilgrims and Jamestown and things like that, where when they started, they had, tiny little streets and things like that. You're talking about cities that were planned in the 1800s, and so they automatically planned a really rectangular grid of streets, and they named all their streets like 100 north, 200 north, 300 north, 100 east, 200 east, 300 east. So when you got there to a new place and you needed to how do I find this place? I mean, the address was a direction. I lived at 135 west, 800 north. So you get to the middle of town, you go 8 blocks north, 135 would be a little bit more than 1 block to the left, right, to the west. That's it. So this is just an address. Every point in the plane has got an address, and it's represented by the x, where are you left and right, the y, where are you up and down. Do you remember that? These things a little bit? You may not remember the word relation, because the truth is we don't use that word a lot, because right away we move on to the word function. And we use function all the time, and we forget about, before we define function, we actually defined relation. And this is just an example. Don't copy, please. But it's the example in the book which is showing, it's like when skydivers jump out of an airplane, they experience a free fall. The photos show various heights of a skydiver at different times during the free fall. How can you represent the relation in 4 ways? So let's see. We have the time when they've jumped out of the plane and their height. So when they jumped out of the plane, they were at their highest height, and then you can record based on how many seconds later it is, where are they with the height. So there's a mapping diagram. There's ordered pairs. There's a table of values, time, height. And then if you define for your grid, time is the x-axis and the height is the y-axis, then you could plot all of those points and you can notice, okay, here was the highest point, next point, next point, next point. Do you notice any kind of a shape to that graph? Is it a straight line? These points, do they make up a straight line? No. This would not be a linear function. But after we do this chapter, we go to the chapter on quadratic functions, where the shape of a graph of a quadratic is called a parabola, and it is like this. It's curved. So the next couple words, important words, are domain and range. And you probably would tell me if I asked you exactly these things right here. Right? Domain is the set of x coordinates, and the range is the set of y coordinates. But in terms of the math, when you got this kind of, we usually think of the x coordinates are inputs, the y coordinates are outputs. Good, Allie? Good. So finding domain and range. Right? These are the points actually from that first example, right? It was at the time of 0, the height was 10,000. At the time of 4, the height 9,744. So the domain is the set of x coordinates. So when they say set means you're going to use these curly brackets like that. Those are set brackets. And then you put inside the list of all the x coordinates separated by commas, right? 0, 4, 8, 12, 16. That's a domain. The range is the set of all the y coordinates. Curly brackets, and there's all the y's separated by commas. Domain and range. Oops. So what would you say is the domain of that one? Okay, so the x coordinates, -3, 0, 2, 9, 23. Domain. -3, 0, 2, 9, 23. What is the range? Right, just list them. 14, 7, 7, 0, -18, and -99. Easy, right? So one of the things that confuses us sometimes in the SOLs, we get to the end. Well, I can't really say, we don't get a chance to always see the SOLs themselves. But sometimes they'll put their answer in these curly brackets in a way that's kind of confusing. It's like they'll solve an equation that has two answers. They'll say solve, right? And they'll put those two answers separated by a comma in the curly brackets. And those are like x values. But because you're not used to, you haven't seen them in so long, you might think that's like an x comma y. Right? It's a little confusing because we don't use those enough, but they'll sneak them in. Okay, a function is a particular kind of relation, right? When you define it, you start out by saying it's a relation. A function is a relation, right? In which each element of the domain corresponds exactly one element of the range. Meaning, if you put in a value of x, you get out a value of y, right? You don't get two values. You don't get more than one value. You just get one. To me, I like to define a function. A function is something that works. Because, I mean, that is kind of like another way to use the word function. To function is to work. I mean, if I plug in an input value into an equation like I'm going to work 20 hours this week, how much am I going to get paid? Right? You expect to get one answer, not, well, maybe you're going to get $150 and maybe you're going to get $200. Right? That wouldn't be a function. A function's got to tell you for one value you put in, you get one answer out. It's clear. It works, right? It answers the question. That's what a function is. So in order to identify a function in these formats, right, here's a mapping diagram, right, where now, if you know the mapping diagram we looked at before, it said inputs and outputs, and now they're not using that vocabulary, right? They're saying domain and range, because that's what it is. Right? There's going to be arrows taking you from elements in the domain to elements in the range. And in order to know whether this represents a function or not, we want to know that for each member in the domain, it only points to one y value. So would you say that that's true for these three? What would make it not a function? What would you be looking for here that would tell you that it's not a function? If you had two arrows coming from the same x, that would tell you it's not a function. In this case, boom, boom, boom. It's just one arrow coming from each x. That means it's a function. Right? How about this one? Do we have just one y value for every x value? And what you're looking for is, are there any repeated x values in the domain? Okay, so there's a 4, -1, but there's a 4, 1, which means it's the input of 4 is pointing to two different y values. That's not a function. So when you've got a finite set of points like that, I mean just a certain number of points, then you can just by inspection look, right? In a mapping diagram, look for more than one arrow coming from the same value of x. In a set of ordered pairs, look for repeated x values. I think I got another. So what do you say about these? Is this first one a function? Because, yeah, you got two arrows here coming from 2. So 2 goes to -3 and 2 goes to 3, so that means not a function. Right. And how about this one? Do you see any repeated x values? Right. So there's no repeated x values, no repeats, means function. Right. It could be that every x value points to the same y value. It'd be kind of like, you know, if I offer to go paint your house for a fixed amount of money, right? You say, well, how much will you get paid if it takes you 1 day? $200. How much will I get paid if it takes me a week? $200. You know, I mean, it doesn't change, but it's still only one value. It's still clear how much I'm going to get paid. It's always a fixed amount, right? That's a constant function. So yeah, it's okay. We got 14 repeats. That's okay. Right? Y's can repeat, X's can't. Okay, but honestly, mostly where we will be using domains and ranges will not be with a finite set of points. It'll be with an equation. It'll be with something like this, where you have both an X and a Y. And, you know, there's infinitely many points. Every point you plug in for X, you're going to get another Y value, meaning another ordered pair. There's infinitely many of these things. There's no way to like write down an entire list and look for repeated X values because it's infinite, right? And that would never work. Right, this is the graph of Y equals X plus 1. How many points make up that line? Infinite. right? Infinite. It's not just here and here and here. Every point, every place you could put a pen, there's another point. And you could imagine 2 points that are so close together that you can't see space between them, but then you zoom in and there's space. So there's points in there too, to infinity. Right? There's infinitely many points in any little segment of that line. Just keep drilling down and there's more. So there's infinitely many points on that line. No way to write a bunch of ordered pairs. So we need another way when our relation or function is being represented by the graph of a straight line. We need another, or a continuous line. We need another way to judge whether or not it represents a function. And that is called vertical line test. Right? A vertical line test is where you imagine the graph you've been given is being intersected by a vertical line. Is there anywhere on that graph you could imagine that would cross the graph in more than one place? Right? For example, here, if I had a set of ordered pairs represented by this shape right here, clearly I can draw a vertical line through it that intersects in more than one place. Right? That would be an example of failing the vertical line test, because for the same x value, right, the x value is the distance to the right, how many different y values are there? 1, 2. Not a function. Now, could you imagine anywhere on this graph where that wouldn't be true? Could you draw a straight line that only intersected in one place? Where do you say, Deshaun? Right there. Right? What if I drew a line right there? I mean, that would pass a vertical line test, but it doesn't matter because somewhere on that graph it fails a vertical line test. It's not a function. Right? Right? This is not a function. Okay, what about our graph we had on the previous slide, which is this? Would that pass a vertical line test? Could you imagine any place that you could draw one vertical line and it intersects in more than one spot? No. So that is a function. Okay. So what's the only straight line that would fail a vertical line test? A vertical line, right? If you have a vertical line, then clearly it fails the vertical line test, because for the same x value, how many y values do you have? Infinitely many, right? Infinitely many. What about a horizontal line? Would it pass a vertical line test? Sure, right? A horizontal is like the constant function I just mentioned, right? For every x value, you get the same y value. But there's no way to cross it in more than one place with a vertical line. So horizontal is okay. Vertical is not a function. Right? So we know what is a relation, set of ordered pairs. We know what is the domain in the range, the x values and the y values. We know what is a function. We know how to check for a function, even if the function is represented by, or the relation is represented by, a graph of infinitely many points. We do a horizontal line test. Okay. I guess I had one more in here. Would you say that this first one represents a function? Right? No. And they've drawn the horizontal line already. How about the next one? Absolute value? That's a yes. The next is a graph of a set of ordered pairs, but still the same test will work, right? Does it cross more than one point with the same vertical line? Yeah, right there. So that's a no. That just copied out of the book. How about a circle? Is a circle a function? No, not a function. Fails a vertical line test, right? Once, twice. That's a no. How about this set of points. Does any of them look like they're on the same line? No, that's a function. How about this graph? Can you imagine any place where a vertical line crosses more than once? No. I mean, yeah, just once, so that's a yes. Okay. So the last thing that we talk about is called function notation. Now that we know what a function is, we have function notation, and it's specifically for, equations. Right, this y equals 3x plus 2. In function notation, you would say f of x equals 3x plus 2. So you write it like this, f parentheses x and parentheses. And you read it like f of x. But you're going to think of f of x as y. I mean, it's the same thing. Y equals 3x plus 2. F of x equals 3x plus 2, same thing. Now, something to keep in mind, because we do make mistakes on this, I've seen it, is that when you look at this function notation there, right, that is not a multiply. Okay, that's not, like the parentheses there are not saying f times x. It is a function, it's how you use a function, it's f of x. All together, can't be peeled apart. Right? You'll never try to split the f from the x there. Not a multiply. I've had students try to divide by the f to solve for x. That doesn't work. Not a multiply. Now, when you're given a function notation like f of x equals 3x plus 2, then you can evaluate the function by plugging in a value of x. Just like we evaluate an expression, right? You plug in a value for the variable, right? F of 1 would mean substitute 1 for the x, and then evaluate, order of operations, right? F of 1 is 5. 3 times 1 plus 2. Right? That tells you you've got the point on the graph of 1, 5. Right? We input a 1, we output a 5. Okay, let's graph this thing by making a table of values. So the first question, we do this a lot in this class, because at the beginning of each chapter, which is a new kind of function, we don't know what the shape of the graph is, so we try to plot some points and see whether we could, determine what is the shape of this thing. So the question is, well, which values should I plug in for x? Well, x is the input. You get to choose, right? You get to choose. So, I've got my graph here is around x equals 0. So how about if I just take like 3 points? I'm going to choose, because I get to choose the x values, -2, 0, and 2. Right? For each one of those now, let's calculate the y by plugging into the function 3x plus 2. Right? So this one will be 3 times -2. That was wrong. -2 plus 2, which is -4. Let's plug in a 0. 3 times 0 plus 2. 2. 3 times 2 plus 2, which is 8. So those are 3 points, right? This is the point -2, -4. This is the point 0, 2. This is the point 2, 8. And I did make my grid big enough, but so we know how to graph these. Where would I find the point 0, 2? X equals 0, Y equals 2. Starting here, where should I go? Go up 2, right? The X is 0 is telling you don't go left and right, but the Y is 2 telling you go up 2. Here's the point. Okay, how about the point 2, 8? Right 2, up 8. I think I got that one. 1, 2, 3, 4, 5, 6, 7, 8. About right there. So let me just connect those. How many points do I need to graph a line, a straight line? 2, right? So that's enough. We can do with those 2. My other point would have been way down here. So let me do this. Come on. So remember, the main point of this is you choose the X values. Because I get that question a lot at the beginning of every chapter when we're plotting, and you're looking at an example in the book, say, where did they get their X values from? They just chose them. They made them up, right? Then maybe they made them up for a reason, they picked those X values, but they get to choose. We always get to choose the X values. Okay. So let's evaluate. Here's our function, f of x equals negative 4x plus 1. How would we find f of negative 2? Say again? In the place of the x here, put negative 2. Negative 4 times negative 2 plus 1, which is 9. How do I find f of 0? Plug it in. F of 0 equals negative 4 times 0 plus 1, which is 1. And then f of 5 is negative 4 times 5 plus 1, which is negative 20 plus 1, negative 19. So evaluating functions. Now, if you haven't done that before, maybe that's a little bit new. We end up doing this a lot. In every class from now on, we don't always just plug in numbers, though. Sometimes we have to plug in things like variable expressions and calculate. But that's not part of what we're doing at this moment, so we won't worry about that. Later in this class, we will do it. Okay. And I think there's one thing that I didn't say that I'm just going to add to this slide right here, which is, or maybe I'll go back. X is the independent variable. Y is the dependent. Right? Because the equation is solved for y. In order to know what y is, you got to plug in an x value. So y depends on x. That's why you call x is the independent variable, y is the dependent variable. And you need to know that, because even in your calculator, we will use tables of values in here. If you go in your calculator above the window where it says table set, second table set, that's what this means right here. That's why that says independent and dependent. That means x, y. So you get to choose. In this case, it's telling you, do you want it to automatically populate a table of values, or do you want it to ask you for x values? But that's what that means. It's kind of embedded in all this, independent and dependent. So that's what we did. We graphed. We identified functions. We did domains and ranges. We used the function notation. So the homework, which honestly, I know that we have like 15 minutes left. You could clearly be done. It's very easy.